Thanks for the invitation. I'm excited to be on Zoom. I would prefer to be there in person, but it's a fairly long flight. I'm from the West Coast, and as John mentioned, I'm the founder and CTO of the company at Functionize. We're working on some really interesting deep learning, and today, this sort of is just covering deep learning in general. This is not a product pitch. It's not anything other than just sort of deep learning and its role in how it works, today generally across industries and its relevance to testing and kind of what we're seeing in the market, what we're seeing in the tech, where things are heading. So I'm really excited about this topic. I'm going to jump into it. Again, it's a deep learning topic. Please make notes of your questions. I really love questions, and at the end, I'd really love to have an interactive session as well. So again, I'm Tamas. I'm basically an engineering background. I did a lot of deep learning and ML and building enterprise software previous to starting the company. And the topic will be, as I mentioned, just informative technology, just what's happening with AI, the state of AI in testing, how it's different from traditional software. And I'll cover these in high level, but hopefully we'll get the point across. Some of you might be familiar with some terms, but I'm going to try to put that down, some basics if you are not. And then specifically, how do we apply deep learning in testing? And then specifically, what would an application look like in deep learning today? And then sort of where the market's heading. And so my first slide is a super interesting slide. And this is really about the why. And if you look at, how the market has evolved, just generally, again, this is not testing, just, if you look at the S&P 500, like in the 1960s, the average life expectancy of a company was 75 years. And shockingly, by 2020, it went down to 15 years. And I think that as innovation speeding up, that potentially could be going down, so that lifespan could potentially drop. And really the question is why? And, I think that the simple answer is innovation. So if you look at the speed of innovation and the rate of change and its impact on companies, it's quite dramatic. And I think it's accelerating. So, I just took a company, Kodak, because it has some history. And again, it sort of missed the digital transformation. They were amazing with film. Some of you might remember using old non-digital photo cameras and taking photos, and Kodak was the absolute best, and they kind of missed the revolution, and you could see that just the dramatic impact on their business, and they're quite irrelevant today. If you look at today, the market is amazing stuff going on. I mean, I think there's blockchain, Web 3.0, there's genomic sequencing with amazing stuff, obviously 3D printing, robotics, energy storage, autonomous vehicles. And I put this circle in the middle. Actually, I didn't put this circle in the middle. I took this from a fund that focuses on innovation. And it's really interesting how AI is sort of in the middle. And the way I think about this is that AI is the glue. So if you look at most of these technologies, big data and AI is at the center of it. It's what's gluing it together and driving it. But again, I think generally speaking, if you look at the market, we've probably never seen as many, sort of disruptive technologies happening at the same time as we see today. And, when you look at the impact, I think that easily we could argue that the impact of AI is at least as big, if not bigger, than the steam engine or electricity or computation itself as it came in the 1900s. And so I look at this as the most revolutionary technology today. It's driving a whole bunch of other industries, and who knows what the future holds for us with AGI and so forth. But certainly that's also in the near future as a threat. And if you look at that as sort of impact on GDP, right, then this is just a 8-year, 7-year time horizon. If you look forward, it's GDP impact. This is something that again I took from PricewaterhouseCoopers, big firm. It's close to $16 trillion over the next 6, 7, 8 years, versus where it is today at 3 or 4. So you're going to see this market sort of, 4x, 5x. And what I love about this slide is that you see it's a very big portion of that is quality. And the quality of products, I think, is going to become paramount for all companies, simply because of the competition and the speed of innovation and the ease of which you could start companies today and get to market. So, so what do you do what happens if you ignore this, right? And again, I just took these off, so it's not something that I'm saying, but it's something that other smart people are looking at the world. But I certainly am a big believer that if you're not embracing these innovative technologies, you're going to very quickly go out of business. And again, this is just an interesting slide from Accenture that 75% of the executives believe that they're at risk of going out of business in the next 5 years unless they adopt and start scaling AI. And so this is a slide, a couple of slides, a quote from Gartner and the World Quality Report, very similar, right? So we're going to see adoption in AI over the next 3 to 5 years, and by 2025, Gartner thinks 70% of the enterprises will have implemented or using AI-augmented testing or AI-based testing. And in the World Quality Report, we can see this as the strongest growth area for testing. So that's really the point of the talk today. And sort of what is it? How does it work? I get a lot of questions from a lot of practitioners of, okay, what it is, where does it go? How does it work? And how do I wrap my head around it? So hopefully, I'm going to be able to answer some questions on this, and certainly, again, please be sure to jot your notes down and come with some cool questions at the end. So here's if I'm just looking at testing and then specifically automation, this goes back maybe 60 years or so, and sort of last 20 years, 25 years, we saw some scripted automation, sort of. Maybe in the last 5 to 10 years, we started also low code coming along, which means that some tools that tries to abstract away some of the code that we have to write. And I think today we live in a world where AI-assisted deep learning is there. And I see the very near future, we're going to see a lot of also autonomous capabilities that's going to come from AI. Now, that said, I think that the human component is going to be extremely important. So when I look at the market, I think that most companies need a lot more. So this is really going to supercharge you guys, is going to supercharge people that have domain expertise to use these tools the right way. So I want to just quickly touch on what machine learning is. Again, most of you will be familiar with this concept, but I want to define a couple of these terms so it sets the stage for some of the topics that I'm going to be covering. So when we think about machine learning in general, so you hear AI and machine learning. So what's the difference? I look at machine learning as a fairly broad term that describes, some sort of algorithm that's learning from data. It could be some simple algorithm. It could be something fairly complex. And I'm going to pit it against traditional software, which is basically something code you write. You're fully in control. Every line executes the way that you describe it. And, you guys are familiar with this. This is, just something, maybe file statements, some control structures, some functions, and you define what those functions do. And then so again, going back to what machine learning looks like, you could just think of machine learning model as a function. It's very simple. It has an input. It will do some computation on that input, and it will give you an output. And in order to do that computation, it will be fed data, right? So the difference is instead of us defining what that function does, we're going to take data and we're going to train some sort of model that's going to do that computation. And you can think of this, and again, just I wanted to find some good graphic to show that these deep learning models are basically incredibly complex functions. The reason we don't write them, because they're arbitrarily complex. They could be extremely large. There could be millions, hundreds of millions of equations in there that do something, right? So it's not feasible for us to write it. It's not practical for us to write it manually. So, and just a couple of terms, just so we're all familiar with it. There's supervised learning, which is basically a model that learns from a labeled data set. Again, could be a picture, could be an image, but it could be in testing, could be maybe we're going to label some input controls so a model could recognize foreign elements or something similar. So we take data that we humans label, and then we train on these labeled data sets. And then there's unsupervised learning. So you guys are probably seeing ChatGPT. At the core of the language model is a perfect example of an unsupervised learning model, which just takes a very large amount of text and it just builds a predictive model. If I have some sequence of tokens or words, then what's the next probabilistic word that comes? So you don't need to label anything. The corpus of data kind of kicks out the answer that you're looking for. So it's an unlabeled data set. These data sets can be very large. And I'm going to be talking about how some applications specifically in testing on these. And then another one, and I picked these because these are some of the most popular, some of the most powerful kind of high-level categories and ones that we use internally here. So something that I'm intimately familiar with that I could answer a lot of questions on. So the reinforcement learning model is a model where the model is trying to maximize some reward function. So we try to compute, let's say, some good action versus a bad action. We try to give it some score, and then the model is trying to iterate over some activity or some function that will give it the highest reward possible. And then here I'm differentiating between machine learning and deep learning specifically. Like machine learning, again, is very broad. It can take any function. It could be very simple, linear regression, let's say. Whereas deep learning, where the whole concept of deep learning is taking this concept of the neurons that we have in the brain and the activation function in the neuron, and we're structuring it basically. These neurons all connect to each other, and there's many different deep layers of it, depending on certainly obviously the size of the model. And it's trying to mimic sort of how the human brain works. So collectively, I'll just call that deep learning. And deep learning is interesting because, again, what kind of how amazing the results are. So if you look in last 5 to 10 years, really what's been happening in the market is people just scaling up the models, right? So as compute costs are coming down and storage costs are coming down, and cloud compute became available broadly, then we can basically scale up models. There's a couple of innovations like transformers, but fundamentally what sort of everybody's doing also in the valleys, scaling up very large data sets, and we're getting incredible results with that. Again, ChatGPT is a perfect example, but we're seeing very similar things happening in Functionize. So I want to talk a little bit about the use cases, right? So, where would you use deep learning? And I think that the simple way to think about it is use it when you have something of high complexity. Again, going back to what I showed earlier, sort of a very complex function, something that would be really difficult to code up, something that would have a very large number of edge cases, sort of a very complex problem with a lot of edge cases, if you think about like a decision tree maybe. So that's an area where deep learning can work really well. As I mentioned, it works well when we have large data sets. So I think for deep learning, it's not always a requirement, but in many cases, to really get state-of-the-art results, you need very large data sets. So you work with large data sets. And then finally, sort of these large data sets, if you have them, can lead to some really interesting generative use cases across all boards. So including in testing, how would we generate new test cases potentially, or identify lack of coverage. And what I would say again is that it's really complementary to the more traditional approaches. So now I'm going to get a little bit more specifically of these use cases in testing and kind of testing in general, what we're seeing in the market. And when I went out of the internet, I wanted to find a single graph, just sort of like how your code complexity has grown over the years. And I decided to stick to this slide. It's quite incredible. Like every single line is up and to the right. Most of these are exponential. And if you look at it again, the screen might be pretty small, but these are various different sort of, code complexity in automotive industry, code complexity in, developers, code complexity in, the software industry or cellular phone industry. And everywhere what you're seeing is just incredible exponential explosion of code, number of lines and code complexity. And along with that, we also are seeing exponential growth in data. So you're seeing just an amazing amount of data that's being generated by applications, by by users and all sorts of stuff, which all has tremendous value, but also presents massive challenges, both from the testing perspective as well as building software perspective. And if you think about what, how are companies responding to this? And one way that they're responding to is trying to adopt these low code solutions. It's simply because what we're seeing is that companies don't want to own that headache of having to build and deal with that massive code complexity, both again from a build perspective as well as a test perspective. It's a massive burden. So in order to try to keep up, you're introducing these low code solutions that help you get there faster, and you actually at the end don't really own the underlying technology, which is making your company not have to deal with this. Because again, it's not uncommon to see 1,000 applications in a large enterprise these days, and all of those need testing. So it's quite crazy. And here I'm going to just sort of touch on the common testing challenges that we see. It's going to be important just in the context of how do we apply maybe learning to try to solve some of these problems. So we see still slowness. So slow is something that we see all the time, whether it's execution, whether it's testing cycles, or again, ability to be able to tack on in a sort of an agile process, tack on testing at the end. It's pretty slow. We see a lot of complaints and fragility. I build my test cases, they work today, but they don't work 2 days later, or they don't work a week later. I very commonly talk to executives that they say, well, gee, we have a lot of test cases, but half of them don't work, or maybe 40% of them don't work. And, we don't really know why. We don't have time to go back and, figure it out. Another one that we see still also quite a bit is lack of coverage, whether it's lack of coverage for automation or just, lack of coverage in general. But, companies, again, with that, if you think about that exponential graph, are struggling to keep up with coverage as well. And then, a lot of the approaches that we take today are also error prone. So still, despite of the effort, despite the right coverage, we see escape defects, we see problems that make it into production. And finally, we see companies wanting to get to CI/CD, but not really able to. And that comes down to, again, maybe lack of expertise, lack of coverage, fragility of the test cases, and, anywhere from they don't work, where we try to make them work, but the developers don't trust it. And it's, some combination of these. The other piece that's really interesting is that testing really provides a large scale challenge. So I just took a medium-sized sort of orchestration or test suite, if you will, out of our system. Maybe about 500 test cases is pretty average for a medium-sized company, maybe on an application. Average maybe 80 steps per test case. And if you take that, if you just multiply that up, it gives you about 40,000 steps in an execution. Now in Functionize, we take about 4 screenshots per step, trying to get these states of the application. So that's about 160,000 images. But even if I just stick to the 40,000 images, that's potentially 40,000 page views you could look at, or you try to validate, which is absolutely massive. And that's just a single execution. So we also see the scale challenge and micro changes in how do I test most efficiently when I have a small change in my app, and then again I would have a very large number of potential sites to look at. So I talked about sort of fragility and test maintenance. This is probably the number one pain point that we see, and I just put it here sort of to show you sort of traditional approach. On the left side, maybe some script that performs a flat sequence of steps. On the right, maybe some more modern wrapper types. Generally, some companies have solutions that might do some try and fail. Okay, if you do this, if that didn't work, try this. If that didn't work, try that, which we call these kind of try and fail approaches. But these are all still pretty brittle and still error prone, and it's not a great way to scale up your testing. And they lead to what we call this test debt. Again, we talked about fragility maintenance. You guys are probably pretty familiar with the common pain points. We at Functionize just call these test debt. And test debt is really as that if you think about scaling out your testing, and again, if you think about, hey, I'm a large enterprise, I have dozens, hundreds, maybe in some cases thousands of applications to cover, the more test cases I build, the more maintenance burden I have, the more test cases I have to keep up to date, and the more basically my time is used over time just trying to maintain what we have, and kind of just basically very quickly that outstrips capacity to get new coverage in, to cover new features that are coming out or acquisitions that are coming in, and ultimately we just see this as being the number one driver to automation projects that fail, or regression suites that just end up not being used or get dropped, or just eats up all of the time of the team. And so generally speaking, we look at the market is still pretty challenged. Again, shockingly, there's still a lot of companies that do just a lot of manual testing with little scripting. Again, some do some scripting where they see this maintenance pain, and even adopting shallow AI with some simple logic still remains a fairly large challenge to maintain and get to success. So this is where we believe that deep learning is going to change everything. And this is where deep learning can also help us scale up the testing. So how does that look, right? What does that look like, right? So one key area that you could think about in deep learning is its ability to generate a large amount of data, and from that data help you with maintenance, or help you generate new test cases, give you new coverage. Another area is independent decision making. So when you think about running a deep learning engine to do your testing, you can hand over a lot of the decision making that's mundane, and that kind of independent decision making can make your test smart, dramatically reduce the fragility. And then lastly, it's the model's ability to be sort of auto-regressive. If you think about applications, they evolve over time. Changes are coming in on a day-to-day basis. Developers are pushing code in an agile fashion. Some companies are pushing code multiple times a day. We would like to have our models to be able to learn and adapt, both from changes in the application and changes from input from the developer or the tester. And so what we're seeing is that when you roll out a deep learning system over time, this basically reverses, right? So initially you're going over time to the right, and with the more coverage you're getting, more test maintenance burden. And over time, as you're deploying the deep learning model, that actually reverses itself, because the more you run the test, the more the test learns your app, the less maintenance you have to perform. Again, there are legitimate cases when you have to do, but it could solve basically 80-90% of the fragility and the day-to-day pain points that you could see in testing. So I'm going to get into a little bit. There will be a couple of more technical slides here. I hope that you guys will enjoy. But again, so our purpose here is to see how deep learning can address the key challenges. How can it make us from slow to fast, from fragile to stable, from low coverage to increased coverage, from reduced number of errors, and ultimately get to successful CI/CD and get us there quickly. And in order to kind of walk you through how that's done, I'm gonna kind of walk you through how a deep learning agent looks at testing and test cases. And you can think of every test case is just being part of a simulation of a user workflow. And when you think about the user workflow, it contains a series of inputs with some deterministic expected outputs. And these outputs are operating on the app, and the application itself is just responding to the inputs. Maybe I put my mouse over a tab and something changed in the application. So really the application you can think of as just a state machine that's responding to the inputs, outputs, and changing its state. And so the step one in a deep learning model is to be able to represent these states. So the way we think about the application as a state machine, in order for me to perform input output, I need to be able to measure and need to be able to represent these states. So that's sort of the first step. The second concept is, as I'm performing these input outputs, basically, it just becomes a series of like a decision tree. I go to this page. If this data shows do this, perform this action. If that data shows perform this action. And basically a user journey or a test case essentially is a sequence of these input-outputs. Some of them are dynamic, some of them are conditional, but really they just represent like a Markov decision process. So it's a decision process that works on the state machine, which is the underlying application. And in order for it to understand the application, it needs to, so this is what we're seeing, and this is sort of what we're representing in our models. It needs to be able to see or understand pretty much everything that application has to offer that normally a manual tester would look at. So it needs to understand the interactivity of the application. Is it ready to go? Is it not? Maybe it's loading something. It needs to understand the elements that are on the page, the objects, needs to be able to recognize these objects, needs to be able to compute visibility, location, render order, network traffic, the type of executor that it could use. How do I scroll to the element? Is it covered? Which part of the button could I click? And ideally, you're taking these multiple dimensional computations, and ultimately you could arrive at an action. What action should I take? How do I perform the action? And then one final piece of this is that to be able to evaluate that. So to be able to say, okay, what is the probability that I was successful in taking this action and I can take the next action, or I should go back to some more computation and try to figure out how to do it right. So that's kind of from a model's perspective. The second piece of this from the model's perspective, again, is to be able to dynamically adapt over time and to be able to learn and self-heal from the executions that we take. So it needs to be able to store a lot of data. It needs to be able to understand historically what happened and ultimately construct this high-dimensional data sets and be able to continuously improve, right? So as you're running your test cases and as more and more data builds up, the confidence of these models will continuously go up. And here I just put this out there. So what it looks like, sort of how the model sees an application. It sees basically everything on the page. It can understand in 3 dimensions how these elements relate to each other, where they are, what their properties are. And it literally like sees everything on the page, including hidden elements and hidden objects. And at every state, basically, it needs to be able to compute this entire page in its entirety. And ultimately, this leads to these high-dimensional data sets. So basically, data is represented in all of these dimensions and some more. So what I just mentioned previously, where which is the right element, and then where it's the element located, whether it's CSS properties, whether it's various states, maybe before you fill a form or after you fill a form, the visual styling, the visibility, again, the timing model, the scrollability, structural position. Basically, if you think about it as a tree, network data, maybe some data had to load in order for this to show up and so forth. And then, again, machines don't understand visibility in CSS. So then another key piece that you're going to be performing, or deep learning model needs to perform is to translate this into metric space. So I'm actually showing you what this looks like as data for a single step, for a single state, among many dimensions. So each column represents a dimension, and these are just normalized values, just basically floating point values that then can be fed to a deep learning model. And each row that you're seeing is basically an element. And again, this is too big to fit onto the screen. Now this goes much farther out. It's a pretty large matrix, and these are these matrices that then the deep learning models could learn on. And one other piece that's really important, as I mentioned, is that as you run your test cases, each one of these data points, each one of these files, if you will, like you could think of it as a large CSV file, becomes a time series data point for the execution. I ran the test case today. I could run it tomorrow. I could run it the day after, and so forth. And it forms a time series data set where, again, you can have a series of changes. Maybe you could end up in a state where you changed enough on the page where the original state would have no correlation to the current state. But because you were doing it over time, maybe micro changes that happen little by little, the models could leverage these time series data points in order to figure out the change, adapt to it, and then ultimately, perform all the self-healing and kind of like auto maintenance, if you will, for you. And then the last piece here that's really interesting is that if you represent everything in data, then user interactions also in an application can be then stored, leveraged, and understood. So if you make a change here, I just picked an example, maybe somebody added a new checkbox onto the page, it wasn't there before. Again, for example, in our system, we can just superimpose the data onto a screenshot, and you can just click a button, hey, add this new checkbox to my test case. But it could also be that maybe the model made a mistake, then you can just make an input. And this input, since it's data, it's represented in data, then can be fed back into sort of reinforcement learning models that make it that next time you run the test case, it will be better. It will not make the same mistake it did before. And, just to think about it, this becomes a fairly large data processing problem, because here's just an average data set that I took about an average size test case, maybe about 100 steps, 3,500 elements on the page with the 20 data points collected. We'll compute about 70 million data points for that test case, and you get that just from a single execution. So it's a very large data. As we talked about before, deep learning loves data. So this is actually really good, because ultimately it's going to be driving our models to get better. And so the last point here that I want to make is that, therefore, sort of, if you think about the future, if you think about an AI-based test solution, you really want this to be co-located with your data lakes, because it's too much data to move around. So we see testing happening in the cloud in the future. I think this is where a lot of companies are moving. We certainly are a cloud-first company. We do have on-prem offering, but we are primarily seeing adoption in the cloud. And one of the reasons is because in a CI/CD, you can execute a lot, you could generate a lot of data, but also leverage a lot of data. So you want to take your test execution and you want to co-locate it with these large data points. So in the cloud, you could move a lot of data without a lot of cost and with a lot of latency, and be able to leverage that to make your testing very robust. The last piece that I want to cover here, this is super interesting. And again, I get a ton of questions since the release of ChatGTP. And we've had NLP, and we also have a product line that's on generative AI, which basically can take these data sets, if you will, these interactions, these states, and we can instrument an application, and it could literally take in data from all of the users of the given application. So think about any production app or pre-production app that maybe manual testers are hitting, and you can take this data and stream this data and use this data to train large transformer models to just generate the test. And really, what's really exciting and cool about this type of technology is for the models to learn all these crazy correlations, the type of data inputs, and then the various different correlations in video. If I select this sequence of data points, maybe drop downs, then this is the next most likely step, or this is the type of step that the users have to take. And the way that we think about it, again, is that, in especially smoke tests and regression tests, there's high value tests that you're going to try to create from and make it as small as you can. So you get a lot of bang for your buck. When you run it, constantly in a CI/CD pipeline, you get a lot, what your coverage is, you get a lot of value out of it. But there's also a lot of case to be made for having additional testing. Maybe you don't run as frequently, but has broader coverage. Maybe it's more probabilistic, but it still gives you information and data point and can catch issues otherwise that maybe your current coverage would not catch. And finally here, what's game-changing about deep learning, and what I think why I'm so excited about this technology in general, is that if you look at learning algorithms, like over time, they just flatten out. Whereas, what we're seeing with deep learning is, as you get more data, it just continues to get better, continues to get smarter. So it's super exciting to see us being able to scale up with the data and get better and better and better. And again, ChatGPT is a great example. You guys, all of you probably have tried it, learned it. It's got amazing capabilities. Again, look at the model size is insane. It's like trained on 175 billion parameters and vast. I think it's something like 45 terabyte of text. So it's quite incredible to see this. So it's really the technology is driving the change in the industry. And then, this is what I want to touch on finally, is that, certainly, domain knowledge is lacking, right? So there's a limitation in these predictive algorithms is limitation in models' ability to know what to do. So the domain knowledge, and again, these very vast, large applications still remains extremely important to have smart, testers, but who can drive these type of systems. So we really think about this as the testing industry is going to have a lot more power with the tools, and a lot more power will level up people to be much more. It's going to be more architects. I think if you look forward next 5 to 7 years, we're going to see a lot of test architects. They're going to be thinking cloud, they're going to be thinking scaling containers, and ultimately the world's going to be a much better place because we're going to have much higher quality applications through the use of these tools. And sort of, again, just here's a couple of summary slides that I have, which is, I see the future as deep learning. It's going to be cloud first. It's going to use a lot of data, and it's also going to be very generative. So a lot of the workloads and mundane tasks are going to be eliminated, freeing us up to do a lot more high quality work, which is so desperately needed, both for end users as well as companies. So again, I really appreciate the time today. I hope that this was valuable for you guys. Here's just a couple of takeaways. Deep learning is amazing. You should look into it if you haven't. It's changing, I think, all industries, and the next 5 to 10 years is going to be super exciting. Data is king, and cloud is king. So you want to be able to get good data, and you want to be able to leverage this data to your advantage. And in order to do that and do that quickly and iterate fast, you want to be in the cloud. And we're seeing, these deep learning algorithms able to solve these really complex challenges that I think, if you look back historically, I think products fail to address, making testing really difficult to do. And then the last piece is that, we see generative AI. Obviously, there's a lot of hype around it too, but it's something, natural language processing has been part of our stack for many years. And again, we're working on it, everybody else is working on it. It's super exciting use cases and more use cases that will come out of it that we will see.